So I've got the topic test here for Physics 1. So I've got the formula sheet that you've got right at the back of your exam with 5 formulas, not a lot given. But we're going to use 2 of these today, this one and this one. So let's have a look at the first question. First question's picking out the words that needs to be put in the gaps. So a wave's speed is the rate at which it transfers energy. The regular, so rate, speed. The regular movement of particles in a wave is called an oscillation. The time it takes for one component complete wavelength to pass is called the periodic time. And the number of waves that pass a point is the frequency. So be careful there. Be tempted to put frequency there, but it's the number of waves, and the time taken is called the periodic time. The distance that particles have been moved from their equilibrium position by the wave is called their displacement. So what that means is going up and down. So this is their equilibrium position, and that's the displacement. So that's maximum displacement there, which is called your amplitude. Well, and there we are, it's called this amplitude. Look, we call it this amplitude. So we come to this one now. So one complete wave is a wavelength. That could start anywhere. That could go from there to there, or it could go from there to there in this case, or it can go from there to there. It's just one complete wave. There to there. And then the wave will start again. You got your amplitude, which you just talked about, wavelength, and then the velocity is on the bottom. Match the quantities and their unit. So speed is v, and it's measured in meters per second. Frequency is lower f and italic, and it's measured in hertz. And then you got your wavelength, this lambda symbol, and it's measured in meters. And then I've put the triangle there that connects all these, which I've got from v equals f lambda. Because f lambda are together, I push the v up top, because these are already times each other. So that's why they stay at the bottom, times. Let's put that up there. Next page, you've got 2 types of wave. You've got transverse and longitudinal. Which one's which? Well, wave A is your transverse wave, because the energy or the oscillations or the vibrations move at right angles to the direction of the wave. So the wave's going this way, but the energy that's put in is going up and down, up and down. So it's at right angles. It's 90 degrees to the energy, the direction of the wave. Wave's going this way. And then you've got wave B, which is a longitudinal wave. So you've got areas of compression, which are X, where the wave's compressed, and then these areas of rarefaction there, where they're not so compressed. And the energy moves in the same direction, or you can say the vibrations or the oscillations move in the same direction as the wave. Give an example of a transverse wave, an example of a longitudinal. Well, sound is the big one for longitudinal, or you say ultrasound, and then transverse is any EM waves. So light, you can have radio waves, microwaves, any of those. Gamma rays is a transverse wave. I think you can use water as well, water waves, but I'd rather not go there, to be honest. Wave A is travelling at 30 meters per second. So I've written that there. Write everything you know. Use an equation from a formula sheet to calculate frequency. Well, what is my frequency? Hang on. What is my wavelength? Well, let's have a look at my diagram. My diagram shows me that this whole thing is 1 meter. How many waves have I got? Well, I've drawn a little line in there. I don't know if you can see. So I got 1, 2, 2.5 waves. So for every meter, I've got 2.5 waves. So how many times does 2.5 go into 1 meter? It's going to be 0.4 is my wavelength. And that kind of makes sense there. Because if you times that by 2.5, which because there's 2.5 waves, each wave is going to be 0.4 meters. So now I've found my wavelength. I can use this triangle now. Remember, to cover the one you want. So I'm looking for frequency. So I put my thumb over frequency. Frequency equals V over lambda, which is 30, which is I got from the question, like the speed, and 0.4, which is my wavelength. And it comes out to be 75 hertz. State the phase difference between the points Q and R. So let's have a look at Q and R. So Q and R, it's half a wavelength. So you can see that I've written here, if that's 0 degrees, okay, we know a full white wave, a full cycle is 360 degrees, or 2 pi. So half of that is going to be 180, and then half of that again is going to be 90. So there's going to be, so split up into quadrants here, look. So you got 90, 180, 270, 360. That's your 4. It's never going to be split up more than 4 in this exam. So the difference from Q to R is 180 degrees, or you can say 1 pi, which is there. And then from Q to S is a full wavelength. So Q to S is a full wavelength. So that's going to be 360 degrees, or 2 pi. And then from T to U, the next one, which is on the longitudinal wave, well, this is going to be the peak, and this is going to be the peak if you put it into transverse wave terms. So you know that's one wavelength from there to there. So from T to U is going to be one wavelength, which equals 360, or 2 pi. What is meant by the term coherent? Well, coherent waves, they're going to have the same phase. That means this phase is going to be equal to each other, and they're going to have the same frequency, because if that was a different frequency, if more waves or less waves passing a point each second, it would be out of phase anyway then, so it wouldn't be coherent. Describe what happens during constructive and destructive interference. I think I can get rid of this page now. I'm going to go up there. So constructive interference is where they get that superposition there. It becomes bigger. So you've got this wave moving towards this wave, and they're both on the same side. So they're both on the upper side here. And when they hit each other, this is going to get bigger. Whereas destructive interference, you've got one wave moving on top, one wave moving on bottom. You can almost think of this now. If this wave was moving this way, and then another wave was moving this way, and you've got two. If this one and this one hit each other, then it's going to be a big wave. But if this one hits this one, you're going to get nothing. Okay, they're going to flatten and merge. So when you've got that happening, you can almost think that the energy that's in this takes the energy that's in this, and it just becomes a flat line. And that's called destructive interference. Select the option that best describes the phase difference required for destructive interference. Well, it's going to be at this point, like I said, 180 degrees. So that's why that box is ticked. So it's not going to be at 90. So 90 is pretty much, if you've got 2 at 90, that's where your constructive interference is going to happen. But your 180 happens to be destructive there. I'll keep that at a second. This more relates now, I doubt if a question like this will come up. I think this more relates to the diffraction. But select an option that best describes the path difference. The path difference. So if I had another wave coming in into this one, going in the same direction, which is the best path difference for a constructive wave? And it's going to be where n, so if n equals 0, 1 or 2, it's just going to be times lambda. So half a wave, or even this, like any number put with +1 there, half is going to be an odd number. And that wouldn't work then. So it needs to be 0 or 1 waves. So it needs to really start at 0, which is why this one doesn't work, because you always got a 1 there. But I think for 1 mark, we don't need to go into that too much. Diagram below shows process used in industry. It's called a diffraction. So this is where light gets split by a diffraction grating. It hasn't asked me that, has it? No. The usual question is, how does diffraction grating work? It's probably on another paper. We will go through it. And then mark the bright spots in the pattern produced on the screen with an X. So the brightest spot is going to be right in the middle there. So this is going to take most of your constructive interference there. That's where it's going to happen. So basically, these lines, these arrows show constructive interference. And then anything else, there's going to be a dark spot, and that's going to be destructive interference. How is it used in industry? Do I identify gases? So basically, diffraction gratings, they split up the white light into their different parts, into their component parts, like a prism would. You've got the missing wavelengths then. They pretty much get absorbed by the gas atoms. So that's how they can tell. They use it a lot to identify the gases in stars, because they'll use a diffraction grating and they'll see which wavelengths get absorbed. Because each type of gas absorbs different energies, they can be specific and determine which gas it is. It's very clever. You would have seen those diagrams, which I can't show you now, but they basically, should I draw one quick? Oh, why is it in green? But you'll have these sort of patterns where these lines represent a different frequency or a different wavelength, and you will know which gas it is, because usually that's the bit getting absorbed on our absorption spectra. Anyway, we will come across that in another question. Draw the third harmonic of a stationary wave. Well, a stationary wave, you're going to have antinodes and nodes. And you can see I got it wrong first of all, but your antinodes are anywhere that's not on that normal line there. So your nodes are everywhere. So you're always going to have one more node than an antinode. So you can see I've got 3 antinodes here. Third harmonic is going to be 3 antinodes. Therefore, you've got 4 nodes. You've got 4 bits crossing. You can almost think of that as destructive interference, and then your antinodes as constructive interference. Describe how a stationary wave is formed. Well, a wave travels backwards and forwards along a string and interferes with itself. So I don't know if you can remember me doing this in class, but you're gonna have a fixed spring or a fixed string at one end, so someone's gonna hold it tight, and then I'm gonna be doing the transverse where the energy's at right angles, and then that's gonna rebound back, and the areas where it comes into contact with itself at an antinode is going to be constructive, and the areas where it interferes with itself at a node is going to be destructive. And I think I've said that there. Nodes appear at points where there is destructive interference, antinodes at points where there is constructive interference. How does a trumpet use a stationary wave to create sound? In very much the same way when you've got an open end. So stationary waves set up in the air by the trumpet's horn, and then many possible harmonics are produced in the horn, producing many frequencies that sound at once. And then this last question for 3 marks towards the end of the topic test. It's going to be slightly harder now. Tension on a string is 15 newtons. 15 newtons tension is a force, and you've got 2 meters in length, and it's measured to have a mass of 15 grams. This must be in kilograms, first of all. I don't think it's a lot of marks for the work you must do here, because I would have said that's a mark in itself. Then you use this equation from this page here, where your speed is tension over mass per unit length. That's that U, or the mu. But they don't give you that. You need to kind of work that out. So you've got 2 meters and 15 grams. So mass per unit length is going to equal your mass over, so it makes sense because it's like kilogram per meter, so it's mass per length. So you've got your mass of 15 grams, which needs to be converted to 0.015. So be smart, mate, stop being done. So be smart, mate, stop being dumb. I'm going from small to large, so I need to so from small to big, I need to divide by 1,000. So that's what I've done. To divide 15 by 1,000, you're going to get 0.015. And then that's over your unit length, which is 2 meters in this case. And this comes out to be 7.5 times 10 to the minus 3, or 0.0075 there. And then you just put that now into the formula. So you got your tension is 15 newtons, 15 on top. Your 7.5 on the bottom, which we calculated, your mass per unit length. And that comes out then, once you take all the square root and everything, is 44.7 meters per second.